Good morning, good afternoon, good evening, everybody. Whatever day it is, Sunday, Monday, or even Algebra Tuesday, I hope you guys are doing great. And thanks for joining us today to talk a little bit more about polynomials. If you recall from the last set of notes, we've been talking about polynomials and kind of how they behave, some of the deeper patterns that go into them. If you have done your homework, you should be familiar with the fact that polynomials can come in several different flavors, several different forms. We've talked a lot about vertex form, where if you have x to a degree, that kind of tells you more about the end behavior. It flips back and forth between odd directions, opposite directions, and even end behaviors, which would be in the same direction. So odd degrees go in opposite ways. Even degrees, if I flip it up one more, go the same direction. And one thing that's kind of interesting, as your degree gets more extreme, it starts to get a little bit more squarey. As your degree becomes smaller, it's a little bit more curvy. And so that's kind of a big trend for polynomials, but only in vertex form. Now, the reason that we would use vertex form is because it allows us to put directions in very easily. If you put a negative in front, you know that's a reflection. If I go ahead and add some grouping symbols here around the x, and then I go ahead and try to move this left by adding any value, that's pretty easy to do, and it's easy to pick apart and know exactly what shape you're getting. But overall, these shapes are fairly simplistic, okay? They aren't the most interesting things in the world, and that's because they all relate directly back to their parent. Right now, my parent would be y equals x to the 19th power, so it's just whatever your degree is. We also talked about, in that set of notes, standard form, a, b, c, d, e, f, g. If you just kind of line them all up, all their pieces, all their terms. I liken this to, kind of riding on the bus. You have lots of people on the bus, but really the person who's driving the bus is always up front. And so right now the degree would be 2, and that is a quadratic. That's a squared polynomial. And sometimes as we get larger and larger, it becomes a little bit more interesting what happens in the center of the graph. And that's why standard form, ABC form, really hard to visualize ahead of time. A lot of these other pieces play a role with the humps and the bumps and the curves and the waves and all the stuff that you get in the middle. Overall, with the standard form, however, you can tell that the degree is even. You can tell what direction it is going by the front or the lead coefficient. And then also the reason that this is important is it tells you the y-intercept, 5. So whatever that constant is at the end is what's left over when all the x's zero out. Then you're just left with the number. So standard form is not as useful, if you will. It's not as easy to graph ahead of time. You have to know some deeper trends in math to know a little bit more about how these shapes will behave. And so that's where today's lesson comes in. We're going to be graphing polynomials in a third format, not vertex form, not standard form, but in what we would call factored form. And we've dealt with factors before. When we factored quadratics, we really broke them into chunks. So starting off the notes here, part A and part B are old ideas, graphing quadratics using zeros. And if you kind of look up here at the top, we have two groups of things. We have an x minus 1 group, and we have an x plus 2 group. These two groups are really beneficial because they help me find my x-intercepts right away. Factored form is great at finding solutions, which are synonyms for x-intercepts. So if you look at the x minus 1 term right here, that is going to tell me that x equals 1. 1 minus 1 zeroes that out, and so I really have a point on my x-axis located right there. X equals 1. The other x-intercept comes from the second factor. X plus 2, if that were to zero out, would come from an x value of negative 2. That happens right over here. Now, besides that, factored form is only good for one other thing. It's telling me if we open up or down, and we just don't know patterns to dig more out of this format yet. The negative in front, you have to realize, is a reflection. And that's going to play an important role here in a second once we get a little bit more information out of another way to write this quadratic. So down below, you'll notice I have a little space for expanded form. Expanded standard form, which is the ABC format, is pretty easy to get to when you're dealing with quadratics or just two factor chunks. All you have to do is FOIL. Double distribute those groups together. So I have x minus 1, and then I have x plus 2 with a negative in front. So foiling this, I have x times x, which is x squared. I have x times 2, which is plus 2x. The inside terms make minus 1x, and then the last terms make minus 2. Now keep in mind that whole thing is wrapped in parentheses with a negative in front. If I combine these two terms in the middle, I have the negative, I have my group of x squared. These two things make plus 1x, because a positive 2 minus 1 is 1. And then I have minus 2 as my little coefficient, my baby, at the end of this format. Just go ahead and distribute the negative in there, which flips all the signs. So my standard form, ABC format, is really negative x squared minus x, and then a negative times a negative is a plus 2. This is kind of a big deal. Going back to my Desmos examples, this was very similar to, what we showed earlier. Standard form tells us the y-intercept here, and it tells us the degree overall. So the degree is 2. We would know that's a quadratic, and we know that it opens down. So quadratic things, even things, will have an end behavior going in the same direction. So we know that overall this is a down-down graph with its end behaviors, and that the y-intercept happens up here at 2. So we can kind of put that information together, 0, 2, and it is a u that kind of comes up and down. So I'll try to get a good U for you. We don't necessarily know where the center is, but if you use kind of some problem-solving skills, it would have to be midway between the two zeros, since U's are symmetrical on the left and the right. So technically, the center is at a half in the negatives. Now, all we're doing right now is just drawing a quick sketch, and you'll see that this is the preferred method for polynomials because they really change quite rapidly. Unless you're dealing with one that you know very well, they tend to surprise you. So we're going to do one more. We're going to do part B, and we're going to see how to look at this polynomial from different perspectives before we start to piece together some big patterns. So it says y equals x plus 2 times x plus 2. If you're talking about the x-intercepts here, it's kind of weird in the fact that you get x equals negative 2 twice. And this should be a little bit familiar to you that if I have negative 2 and negative 2, it's just that one singular point. That means something kind of important here once I go down to standard form. So expanding this out, foiling it out, I have x plus 2 multiplied by x plus 2. Well, x times x, that is x squared. X times positive 2 is plus 2x. I get the inside plus 2x, and the last terms here, 2 times 2, would equal 4. Now, there's no negative in front to have to distribute here, which is kind of nice. There's less work actually for us to do. I just combine these middle two terms to get x squared plus 4x plus 4. Now the reason this is important, the little number at the end, it's my y-intercept. So I cross up here at 0, 4. Probably should have labeled this x-intercept, negative 2, 0. It also tells me my degree. My degree overall is 2. 2 is even. Even things will end up and up since there's not a negative reflecting it to be down, down. Now, how the heck do I get a U that is fitting this situation? If I just drew something like this over here, first off, that's not a very good U, but second off, I actually created a second x-intercept, and that's bad. We only really have one place where we have an x-intercept. So if you're kind of on point here today, no pun intended, you'll notice that the vertex of our U has to be that point. And there is actually a really cool reason why. You guys know if we have something written out twice, if we have twinsies of that factor, you could almost write it with an exponent. So x plus 2 times x plus 2 is literally x plus 2 squared. But this should look kind of familiar to you because this is literally what we did yesterday in the fact that plus 2 moves this left 2. This is my degree still, and there's no reflection, there's no up or down movements. This is my vertex form, just left 2 from the origin. It's a U that opens up. And so then, as a result, it would cross at 0, 4 if we looked at standard form. Now, all of this stuff kind of fits together in a really interesting way that you can take polynomials and you can change how they look, and you can get different information from that format. The key for today's lesson, though, kind of hinges on what's down below. the idea of an x-intercept. And so we're going to talk about what the heck an x-intercept is. It should be a pretty basic idea to you. It is just the point or points of a function that lie on the x-axis. And one kind of quality that they all share is that their height is equal to 0. That would be their y value. That allows us to do some pretty nice things here. So we're going to need x-intercepts, and we're going to focus on x-intercepts to discover some deeper patterns with how polynomials operate here in factored form. So number 1 here, we have this really curvy, crazy graph. Like, we have never seen anything quite like this. It's a pretty unique shape. But we're going to start off by listing the x-intercepts. And so I might color code these here so we can kind of see what's happening, maybe a little bit easier. It just is more organized. So the first one happens at -6, 0. The second x-intercept happens there at -2, 0. The third x-intercept right at the origin, 0, 0. And then the last one here, which I'll make orange, 4, 0. So we have 4 different x-intercepts. Now, a interesting quality that happens at each x-intercept, the graph is behaving a certain way. At this first one, we go from below to above. The second one, we kind of do the same thing, and we just kind of keep traveling through and through, and then the last x-intercept, we stay on the positive side. And so how the graph behaves is actually revealed a little bit with how the equation is set up. But at which of these x-intercepts does the graph go through? Meaning, which x-intercepts do we cross at? Well, if you saw that first one, we cross at -6, 0. We also happen to cross at the next x-intercept, -2, 0. And so I'm just going to write these all out, the ones that cross, because we'll see kind of a pattern here. We cross at 0, 0. And then the last one does not actually cross. This is staying on the same side. It's not passing from positive to negative, from above to below. And so that is actually the third question. At which x-intercepts does the graph bounce? Well, there's only one of them, and that's at 4, 0. Now, this seems like a lot of work for no payoff yet. And you'd be right, except that you don't know the equations that could potentially make this shape. And that's what I have to give you a little bit more information for you to discover the pattern that could potentially be happening here. But before I give you those equations, let's talk about end behavior. This is something you should be able to get just straight from the picture. If we look at the ends, down and then up, what does that say about the overall degree? Well, they're going in opposite directions, and so the overall degree must be odd. Now think about down then up, what lead coefficient would I be really working with here? Well, that's the default, and so, that's the default, so positive would be the correct answer for that part. So I know it's an odd degree, and it's a positive lead coefficient, and watch what type of possible equations might work here. So down below the graph, you have a little bit of space. These are where I'm going to write the possible equations. And when I say possible equations, I just mean that we would have this overall crossing and crossing and crossing and bouncing pattern in those particular spots. It might be stretched out a little bit differently, or it might be a little bit steeper at certain areas, but overall it's going to cross, 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 and bounce in the correct order. So watch kind of what I write here. Y equals, and then I'm going to color code so you can see kind of how this pattern maybe fits. Notice I'm going to write x and then plus 6 to the third. So my first chunk of this equation is x plus 6 to the third power. Then I have a chunk x plus 2 raised to the fifth power. After that factor, these are all factors, I have just x plus 0 and raised to the first. And then I finish this whole thing off with x minus 4 raised to the fourth power. That is one possible equation that would make this crossing, 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 bouncing pattern. Let me give you maybe another equation that would do something similar. So y equals, starting off the same way, Going to even start off with the same factor, x plus 6, but this time it's to the 5th power. So x plus 6 to the 5th. Now if I go ahead and if I write the next factor, the next group, x plus 2 to the 1st. Then we're going to talk about the next x-intercept, which is x itself. And then I'm going to raise that to the 3rd power. And then the last factor, x minus 4 squared. This would also make a crossing, 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 bouncing pattern. Hopefully you're kind of seeing maybe some similarities between the two equations, but if you're not, I'll write out 1/3 possible equation. Hopefully this will drive it home. X plus 6 to the, let's say 7th power. And if you kind of notice, I paused there and I made up an exponent. That should kind of give away a little bit what I'm doing. X plus 2 to the 3rd power. Now we go ahead, we'll say x minus 0, whatever, to the 5th power. And then the last, x minus 4 to the 10th power. That would also make the same crossing, 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 bouncing pattern at those particular spots. Now, can you find out what's happening? If you're looking at exponents, that's good. You're on the right track. So you'll notice anytime that the graph is crossing through from one side to the other, I gotta be careful with my exponent on the green parts here, but all of these are odd exponents. And so odd exponents do something with their action. They're going to cross, which, think back to how odd polynomials would behave. Back here, an odd polynomial crosses from one side to the other. I need to take that negative off here, maybe to see it better from one side to another, or if you put the negative, it goes from the top to the bottom. There's some similarities with how those things operate. Now, what about the even exponent? Well, back here, I had 4 and 2 and 10. Even exponents ended up bouncing. So that was this action at the very, very end. So the location actually is inside the parentheses. Think about if we had an x value of 4, 4 minus 4 would zero that out. It's kind of the same movement idea from the very first chapter of the year of that x minus 4 moves the graph right 4. That's where we're located. X plus 2 moves the graph left 2. That's why it's an x value of negative 2 makes the graph 0. Even exponents, though, are going to behave like even things. Let me pull back Desmos and change this to an even number like 8. Even things, if I take the negative out, bounce. They stay on the same side. I mean, all the way down to quadratics, literally. It's a very nice bounce. So even exponents have a different behavior, a different action than odd exponents. Even things will bounce. Even little exponents bounce. Odd little exponents will cross. Now you'll notice I'm not calling these exponents the degree because they aren't the degree. And that's the last piece that I would like to introduce to you, the last deep pattern that we can kind of get from these possible equations. We said the degree was odd. Well, let me tell you the actual degree that we would have for all of these. So off to the left, hopefully you have a little bit of space, but the overall degree for this first equation is 13. 13 is definitely an odd number. So that agrees with what we said earlier, with what we predicted. Now what about the degree for maybe the second equation? Well, that would be 11. Now, you might be questioning, how is he getting these numbers? Is he just making them up? No, there is a reason why it's 13 for the first and 11 for the second. Let's see if you can catch on why. The last degree is going to be 25. So what's cool about this, if I expanded this whole thing out, kind of like foiling but supercharged, x plus 6 times x plus 6 times x plus 6 times x plus 6 times x plus 6, 7 of those times 3 of the next things times 5 of the next things, you will eventually get something with x to the 25th power. Yeah, that's crazy that is actually an outcome of expanding or foiling this out. But if you notice, I got 25 versus I got 13 versus I got 11 by adding all of these up. 3 plus 5 plus 1 plus 4. Well, that equals 13. 5 plus 1 plus 3 plus 2, that equals 11. 7 plus 3 plus 5 plus 10, that is equal to 25. So these little exponents add up to the overall degree. You have to understand that overall degree is a big picture idea versus these little exponents are what happens in this area of the picture. And so that's why these exponents have a different name than the degree exponent. And every year kids get these things mixed up, just on accident. They don't mean to. But the exponents that I pointed out here about crossing and bouncing exponents, they are called multiplicities. And that's what our definition down below does. So if I'm talking about a multiplicity, it is the exponent that connects to a factor group. I'm thinking if I want to be a little bit more specific than that, but it probably gets the idea across. Let me give you maybe an example that goes with that. I'll use my x plus 2 to the third chunk from right here. What this means is that I have literally the multiplicity of that factor is 3. So multiplicity is a word that comes from multiples. How many multiples of x plus 2 are there? There are 3 multiples of that thing. So x plus 2 times x plus 2 times a third x plus 2. There is a reason we give names to certain exponents. This is how many multiples of that factor group I have. So back in that last equation, I have 7 multiples of x plus 6, 3 multiples of x plus 2, 5 multiples of x, which is the same thing as x plus 0, or just x minus 0, or just x. And then I have 10 multiples of this x minus 4 factor, that group. So multiplicities are the little exponents that tell you if you bounce across. Multiplicities add up to the overall degree. And those two patterns are extremely powerful. You can look at a graph and you can almost figure out what type of equation would make that shape. So let's maybe summarize some of the overall ideas here. This table down below is almost like a little bit of a cheat sheet. The multiplicity of a factor, the little exponents, well, they could be even, which means that I would have a chunk to an even exponent. And if that's the case, the action with the x-axis will bounce. Now, if I have a multiplicity that turns out to be odd exponents, odd little multiplicities happened a lot in our example, that would look like a chunk that tells you the x-intercept, but it's raised to an odd exponent. Now, those things will all cross. They will pass through the x-axis from one side to the other, top to bottom or bottom to top. Even things stay on their same side. They bounce kind of like if you're playing basketball and you are dribbling, the ball comes back up to your hand. It was from your hand and it stays up at your hand, bouncing. So hopefully you see some of the bigger patterns that go with this type of graphing. It takes some practice. It takes being organized in order to make sure that you get everything lined up correctly. Otherwise, you might bounce in the wrong spot or you might cross over when you're not supposed to, and that can be kind of an issue. Take a moment. If you need to go back or pause the movie, by all means, please do that. But we're going to do one more question before we finish out the notes here today, just to get this idea across of how all these pieces fit. So question number 2, if we look at this. Oh boy, this question is really weird. It seems to never graph above the x-axis, which that's kind of unusual. Maybe let's talk about the end behavior of the overall picture here first. Down on the left and down on the right. And remember, this section is really the only section where you get to use these arrows, so take advantage of them. We're going to go down and down overall. Down and down overall is an even pattern, but it's an even that has been negated. It's been reflected, so it opens downwards. So we know a little bit about how we have to kind of set up our different equations, but we don't know a ton yet because x-intercepts are really the key to getting factored form. I'm going to color code these again one last time. So this first one is -4, 0. This second one is at 0, 0. Sorry about that. The third one happens at 2, 0. And then the last x-intercept 3, 4, 5, 6 is at 6, 0. All right, so just make sure you're counting carefully. If we look at the next questions, what actions are happening at those places? So at which x-intercepts do we cross through? Well, as we go through, I don't see us crossing at any of them. So we would say none. Occasionally you'll get a graph that only has one type of an action, and it doesn't do the other style. So at which x-intercepts do we bounce? You write all of them. If you wanted to write those x-intercepts out, whoop, down there, that'd be perfectly fine with me. But that means something for how we set up our factored form. Factored form equations, y equals, or f of x equals, g of x equals, those all mean the same thing. But if I'm color coding my factors, my groups, I mean, think about it. This was x equals -4. So what would have created that x-intercept? X plus 4. That was something I kind of skirted around on the front, but that's how these two things are connected. All right? They have to make each other and agree. Now from here, think about what action we're doing. We're below and we stay below. That is a bounce action. And so bounce actions will have an even multiplicity, an even exponent. There should be an even amount of them. And so really you're kind of allowed to choose whatever number you want. If you said 2, fine. If you said 4, great. If you said 5, well, no, that would actually make a cross there. That wouldn't be right. But 6 and 8 and 28 would all be perfectly fine exponents. And so every class is always a little different. Normally, if I'm with students, I'll have them suggest a number and I'll go with it. But for this example, I'm just going to choose 6. Okay, something that's even, that's different than the value inside, just because I don't want people to get confused. Now, the next x-intercept at 0 bounces as well. So this is almost like bouncing something off the ceiling. It's never going to get past the ceiling. So if I go ahead and write this factor out, because it's at the origin, I could say x plus 0, I could say x minus 0, those are the same thing, or I could just have an x. Now, because it bounces, again, it will need to be even. So in the background here, I have that gray word, so you can see that even numbers could be anything. Maybe I'll make this a 2. If we move to the next x-intercept, right over here, it bounces. Bounce, bounce, bounce. X minus 2 is what would make this factor. X equals 2 is an answer that comes from that group. Again, this needs to be an even multiplicity. So maybe for this one, I'll be a little spicier and I'll choose 10. I'll choose 10. And that really takes me to the last group. The last group here happens with x minus 6 in the factor. That would be x equals 6 as an x-intercept, and it needs to be an even multiplicity. Even multiplicity could be maybe another 2. You can have repeat numbers, repeat multiplicities. That's fine, so long as they're even, that makes it bounce, 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 and bounce. Now what's cool about this? We can tell the exact degree. 6 and 2 and 10 and 2, that makes a degree of 20. We said the degree should be even. 20 is an even number. Now, I will complain. I did not do a good job with my lead coefficient. And I always seem to forget this until I go back and check. So I would suggest you should check this too. It says that it should be negative because we're ending up down and down. There's not a negative in front of this, and so that's actually an adjustment we would want to make. That negative flips it so that it has the correct end behavior. Kind of a big deal. Put that back up there. Now, what would standard form look like? Well, literally, you would have to write out 6 of these x plus 4s, 2 of these x's, 10 of the x minus 2 chunks, and then 2 of these x minus 6 chunks, and you would have to foil and foil and foil that out. Distribute as far as you can go. Now, that seems pretty ridiculous. I wouldn't advise doing that, and so that's why we have computers, you know? Now, if I go ahead and if I type this into a program like Wolfram Alpha, or if you had a TI program, what I'm doing is I'm expanding the polynomial. That's what it's telling the computer to do here in a second. And so once I press equal, it takes the calculator a little bit of time to do all that multiplying. And it's going to output a lot of stuff here, but the thing we're interested in is this equation off to the left. Look at what's up front. Negative x to the 20th power. We predicted literally the degree by adding those multiplicities. You'll notice after that it's plus 56x to the 19th. That would be a result of foiling all those things. Then it moves to minus 1,464x to the 18th. And so you can see this is standard form. There are a lot of people riding this bus, and some of the numbers, the coefficients, are just gigantic. Now, it's nice. The program here tells us how many people are on the bus. There are 19 terms. It's kind of interesting to notice the last person on the bus is the x squared term, and so I'm missing the x and I'm missing the constant value. And so what's interesting about that, technically, if you wanted the constant value to be in the equation, you could do plus 0. But remember what that little constant tells me about the graph. If it's plus 0 as the number, where do I cross? I cross at 0. So anytime that you have a factor that is an x factor, just a straight up x, you're going to cross at the origin, which means at the very end of standard form you'd have a plus 0 there, which is kind of interesting. So we're not going to write down the whole thing. We're just going to write down the first couple terms, and then we're going to do dot, dot, dot. So y equals negative x to the 20th power, and then it looked like plus 56x to the 19th. And then minus dot, dot, dot. And then all the way at the end, we have the number in front of x squared. Now, in case you needed it, you could do the plus 0. That's kind of there to tell you the y-intercept. All of this stuff goes together, and it is literally insane that it goes together. If I had chosen different even numbers along the way, this standard form would change as a result of that. If you chose really big even multiplicities, you're going to get a really big degree that should always be even, ultimately. Now, there are some more patterns and things that tie in to how polynomials operate. The number of turns that you get is something that we haven't discussed yet. Whether it's passing through kind of linearly or if there's a little squiggle at some of the x-intercepts, that's not something that I've focused on yet. And so there's still more to learn, but this is a huge day for like putting things together. Polynomials can be looked at. Really, it's the same coin, and you have one side of the coin that is factored form, and the other side of the coin is standard form, and both sides tell you slightly different things about that object. So I hope that this video kind of made sense, that it helped you a little bit see how polynomials are just wonderfully surprising. And I really enjoy teaching these lessons in particular just because you never know what you're going to get, and there's freedom in being able to put different multiplicities along the way. So if you have questions, jot them down on your paper. I'd be more than happy to answer those, or if you're watching just online, leave them in the comments. Be happy to help with that and talk a little bit about the math. So I hope you guys have a great day after this. We'll see you guys next time. Take care, everybody.